Change Institute students and faculty to hear about all the great things that everybody's been doing over the last couple of years. I'm not going to take any time here because we're already a few minutes by, but I do just want to let speakers know that you will get some warnings in order to stick on schedule. There'll be a 2-minute warning, a 1-minute warning, and when you get to the end, you get this. So when you see that, just stop. Thank you, and enjoy the symposium.
Hi everyone, welcome to session 1. To start us off, we'll have Allie Balter, a glacial perspective on North Atlantic climate during Heinrich Stadials.
Hi everyone, my name is Allie Balter. I'm a second-year master's student here at the University of Maine. And today, instead of updating you on the results of my master thesis, I'll actually be sharing a beryllium 10 glacial chronology from Northwest Scotland, developed primarily by my advisor, Gordon Brownlee. With funding from the Dan and Betty Churchill Exploration Fund, I was able to accompany Gordon to Scotland last spring to perform fieldwork, and I've been helping him to work on samples in the lab since then. This glacial chronology from the Northwest British Isles documents progressive retreat of the former British ice sheet onto land during the last deglaciation. And while this remains a work in progress, we have so far measured beryllium 10 in over 60 samples from erratic boulders perched on marine crests and molded bedrock, with our aim being to provide a nuanced view of glacier response to abrupt climate change in the North Atlantic Basin during the last deglaciation. And in particular, we place emphasis on Heinrich Stadials. We're interested in Heinrich Stadial 1 and the Younger Dryas. Heinrich Stadial 1 occurred from about 18 to 15,000 years ago, and the Younger Dryas from about 13 to 11,500 years ago. These Heinrich Stadials are traditionally characterized by cold temperatures in the North Atlantic, as seen in the Greenland ice core record, as well as the sea surface temperature record off the coast of Spain. However, other paleoclimate records provide a conflicting view and suggest that perhaps warm sea surface temperatures occurred in the Northeast Atlantic during Heinrich Stadials, and additionally, that discharge from the decaying European ice sheets may have gone into the North Atlantic during Heinrich Stadial 1. This provides a potential model whereby Heinrich Stadials may have been characterized by extreme seasonality with really cold winters in the North Atlantic, but summers that remained warm. Glacial chronologies offer an ideal proxy for testing this hypothesis, as glaciers shrink in direct response to rising summer air temperatures. And therefore, Gordon developed this project in Scotland, right in the heart of the North Atlantic, to get a glacial perspective on Heinrich Stadials. In Scotland, the former British ice sheet terminated offshore Scotland on the continental shelf, and our record can't tell us exactly when retreat began from this outer limit, but based on previous work on marine radiocarbon ages and beryllium 10 dates from islands off the coast of Scotland, we know that retreat began around 20,000 years ago. Our record can tell us when the retreating ice margin reached the modern coastline and pulled back into the former source areas of the British ice sheet into these mountains. So we're building a transect from the coast into the mountains. In these mountains, the record in mountain cirques covers the latter part of deglaciation, including the Bowling Allerud and the Younger Dryas. And age constraints for this time of the deglaciation are incomplete in the British Isles, so we hope to contribute to those. To obtain our surface exposure age dates, we sample the top surfaces of erratic boulders, as Holly Thomas is doing in this photo. We then measure the beryllium 10 concentration and calculate an exposure age using a locally calibrated production rate of 3.91 atoms per gram per year. The earliest moraine preserved in our study area, this map zooms in to Northwest Scotland, showing our study area. And the earliest moraine preserved was deposited at a time when the ice margin terminated partly on land and partly in the sea. This moraine complex was first observed in the 1970s when it was termed the Wester Ross Readvance. And we're focusing on the Altbaya Peninsula part of this moraine. The presence of this moraine suggests that there was a slight pause in deglaciation. And here's a closer look at that moraine complex. 3 beryllium-10 ages from the primary ridge of this moraine cluster tightly around 16.8 thousand years ago and give the time that this moraine complex was abandoned by retreating ice. This retreat is corroborated by ages on erratic boulders inboard of the moraine complex, which gives slightly younger ages, indicating that retreat continued at that time. And I'd like you to note that all of these ages fall during Heinrich Stadial 1. A subsequent pause in deglaciation is marked by a spectacular moraine complex, which can be traced along the shores of Little Loch Broom here and in the mountain of Anchalik. That moraine was deposited at a time when the ice had pulled back significantly from its location on the Alpe Peninsula, but the lower reaches of the ice sheet were still near moderate sea level. Now we'll zoom into the Anchalik Mountain and take a look at that moraine. You can see the moraine nicely in this photo here, but I've also outlined it for you. This moraine was deposited at a time when ice filled this fjord feature, now occupied by Little Loch Broom, and came into this valley pictured here. This offers another view of Anchalik, now looking to the north across Little Loch Broom. And the moraine I showed in the last slide can be traced along this valley wall, as well as on this side of Little Loch Broom. And this cartoon shows the location of the ice when that Anchalik moraine complex was deposited. 10 consistent beryllium-10 ages from 2 neighboring sections of this moraine indicate that this moraine was abandoned around 16,000 years ago, so retreat was underway here during Heinrich Stadial 1. One other valuable piece of information that we can take from this Anchalik moraine complex is an indication of where regional snowline lay at 16,000 years ago when this was deposited. Moraines are only deposited in the ablation zone of a glacier or below snowline. And therefore, we can trace the moraine uphill to where it vanishes to obtain information about the minimum snowline that must have occurred at this time. We found that at 16,000 years ago, the Anchalik moraine was deposited and snowline was at or above 625 meters elevation. And this is intriguing because 625 meters is about up here on the hillside, and we know that all of this ice still existed during that time below the snowline, so it must have been melting during the summers at 16,000 years ago. Continued thinning and retreat of this glacier is seen by these marginally younger ages on a recessional moraine that cluster around 15,500 years ago. The final stratigraphic unit for which we currently have data was deposited during the last gasp of glaciation in Scotland, locally known as the Loch Lomond Re-Advance. We focused on 3 cirques which nourished alpine glaciers during that event. So far, we've collected samples in all 3 of these cirques, but have only analyzed beryllium-10 ages in these 2. And for the sake of time, I'm just going to share the Benmore-Koyak results with you today, but know that the results from Anchalik look very similar. Here in Benmore-Koyak, the Loch Lomond Re-Advance is indicated by 3 principal moraine ridges. And we're just partway through analyzing the samples at this site, but so far we have an age on a erratic boulder outboard of these moraines perched on bedrock that indicates that the ice sheet abandoned this part of the valley around 14.2 thousand years ago. The outermost ridge of the Loch Lomond Re-Advance cluster of moraines gives an age of about 13.4 thousand years. And I want you to note that that is during the Bowling Allerud, so predates the Younger Dryas, and indicates when the culmination of this advance occurred. Continued contraction of this glacier is indicated both by the stratigraphy here, as well as some younger ages that we have so far on those inner moraines. We're looking forward to running the rest of the samples at this site over the coming year, especially these erratic boulders, which are perched on bedrock on the floor of the cirque, and will indicate the time at which the final downwasting of this glacier took place. I'd like to end by bringing this whole chronology together and see what it can tell us so far about glacial response to Heinrich Stadials in the North Atlantic. Here are the records that I showed you at the beginning of the talk, and I've also added Gordon's glacial history here in the middle, with red being times that the ice is retreating and blue being times that ice is advancing or stable. We know that the deglaciation of the British ice sheet began around 20,000 years ago from other studies. Our study suggests that Heinrich Stadial 1 was dominated by continued retreat of the British ice sheet, driven by summertime warming. Also during Heinrich Stadial 1, there were brief interruptions or pauses of deglaciation at about 17 and 16,000 years ago, and those are indicated by the presence of that Alpay moraine and the Anchelic moraine complex. Final advance of glaciers in Scotland culminated during the Bowling-Alarud and predate the Younger Dryas. So although there's more work to be done to finalize our chronology, our results seem to support this seasonality hypothesis, whereby winters may have remained cold in the North Atlantic, but summers were sufficiently warm to sustain deglaciation. With that, I'd like to once again thank the Dan and Betty Churchill Exploration Fund for allowing me to participate in this project. And if there's time, I can take any questions.
Our next speaker will be Aaron Chesler, using ice-penetrating radar to identify Holocene age ice in the St. Elias Mountains in Canada.
Thank you. Do I just hit next?
You got to the questions in a hurry.
What?
You got to the questions in a
I got to the questions. We're done. Thank you. All right. So good afternoon. So our goal with this project was to primarily find a continuous Holocene length ice core in the North Pacific and to see if we can compare recent Holocene change back to the early Holocene when temperatures were similar to today. And so let's look at the global Holocene climate trend. This is a stack from Marcotte et al. In 2013 of 73 different records from both hemispheres. And we can see that during the early Holocene, there were warm periods from about 9,500 years ago to about 5,500 years ago. After this warm period, there was a decreasing trend in global temperatures into the late Holocene, where there were fluctuations such as during the medieval warm period and the Little Ice Age. Then in the 20th century, we have an increase in temperature back to early Holocene values. But within this context of this global climate trend, there's regional variability. And so one way to assess regional variability is to look at one particular region. So we looked at the Arctic, particularly because there's ice cores still there that we can use. And ice cores are particularly useful because they provide a direct reference as to what the atmosphere was doing at the time of its formation. But one particular proxy that ice cores have or contain are melt layers. And so melt layers are important because they are a physical property of what the atmosphere was doing during the time of its formation. And these form when water, so we know that the atmosphere was warmer or increased to allow melting or just rain, percolates through the snow and then refreezes at a depth in the snow layer that just accumulated throughout the past year. And so we can use the melt frequency of these layers to see when there was warmer periods. So during increased frequency of melt layers, it's during a warmer period. When there's a decrease in the melt frequency, then it's during a colder period. And so when we look at the Agassiz ice cap from 1984 and the 1987 ice core records from the Northeast Canadian Arctic, we see that during the early Holocene, there was an increase in the melt percent frequency that were found in the ice core. So during the early Holocene, here we are. There is an increase in the amount of melt layers with a decreasing trend, following that global trend, followed by a recent increase in the 20th century in the melt layer percent frequency. And so this regional trend is mimicking, or not mimicking, but is similar to the global climate trend that I just showed in the previous stat. And so when we zoom in on the late Holocene, we have that same trend. We have late Holocene variability through the past 2 millennia, followed by a recent increase in the instrumental record in the 20th century, following the warming pattern. But when we look at where these different proxies are being taken place, most of the ice cores, which we're particularly interested in, are from Greenland, Northeast Canada, and off of the Barents Sea. And so our goal here is to really focus in on the North Pacific and see if we can add to the record add to the Holocene record of ice cores that are available to understand what the Arctic was doing over the last 10,000 years. And so we did this at 3 different sites. This is from Mount Hunter, which is in Denali National Park. Mount Hunter is down here, outlined in the blue. Will Kochtitzky did these maps. So we zoom in on what's going on at Mount Hunter. This is from Winsky et al. In 2018, and that shows the same 20th century increase in the melt layer percent frequency that we saw in the Arctic trends and in the global trends. And Winsky et al. Interpret this increase in frequency as an increase in summer temperature, in summer temperatures by about 2 degrees per century. And when we look at the precipitation records, we have the same trend. We have increasing precipitation, which relates to warming. And we can see this trend within the past 150 years. If you look up here, the blue is the winter trend and the red is the summer trend. So we have increasing precipitation, we have increasing temperatures in the late Holocene. Now, our question here is, how does the early Holocene climate relate to 20th century warming? And so now when we look to the deeper part of the record, we're still working on this at the moment. The top part of the record is dated with annual layer counting. But as we move to the bottom, we lose the annual layers. And so Carl is in Switzerland right now doing the carbon-14 analysis on the lower part of the core. And within the error margin, we believe that the Mount Hunter Denali ice core will give us a complete Holocene record in the North Pacific. We also took this research to the eclipse ice field in the St. Elias. This is in the Yukon, just borders the US. So let's zoom in here. The eclipse ice field is located right here, and we'll zoom into this image. So the yellow dot highlights the 2002 ice core location, but you'll see in another image, there's a better area to take the ice core in this locality. The green lines represent all GPR profiles taken within the last couple years of the site, and the black dotted line represents the GPR profile in the next slide. And I'd also like to note that this location is an ice divide, so the bottom part of this ice isn't being deformed too much by flow, which makes it a more ideal ice site in a mountainous region where flow is prevalent in glaciers. And so here we have a possible Holocene ice column at the eclipse ice field. I'd like to note that the black dotted line right here, this is the 2002 ice core. These are the bedrock profiles. AD stands for avalanche debris. And in here you can see conformable stratigraphy. And I'd also like to note the Katmai 1912 eruption that you can see throughout the GPR profile. And here is where we believe that the best ice core site or locality would be. And it's exciting because it shows the GPR profile shows continuous stratigraphy throughout the site. And so our third location is King Coal. This is off of Mount Logan, and it's just over here. And here's the site itself. And so what I'd like to note about the site that's particularly different from the eclipse ice field is that we have this flow coming off of Mount Logan into the site itself. And so the GPR profile in the next slide that I'm about to show you is taken from where I'm standing in this picture, or from where Seth was standing in this picture, out across this coal. And so when we look at this, there's something very significantly different than what was at the eclipse ice field. And it's particularly this complex stratigraphy that's coming off of that icefall from Mount Logan. The only area at this site with conformable stratigraphy that would lead to a continuous record, just a continuous record, not a whole Holocene record, would be in this area right here, which only goes down about 150 meters. The deepest site at this, the deepest ice at this area contains this complex stratigraphy that would make it unrealistic to obtain a complete Holocene record from this site. So what are our conclusions from this? So the Mount Hunter-Denali late Holocene ice core record shows large industrial age changes in temperature and precipitation. These are the same increase in temperature precipitation that we're seeing in the melt percent layered frequency in the Arctic and in the global trends. And so we know that the North Pacific is starting to, we can see a relation between the North Pacific, the Arctic, and the global trends that were occurring during the late Holocene. Based on global syntheses from Greenland Arctic ice cores, we hypothesize that the North Pacific is similar to the early Holocene. Because we have this relation between the late Holocene, we believe that we can have the same relation during the early Holocene. The new carbon-14 analyses in the bottom portion of the Mount Hunter core may extend the depth age profile, depth age scale throughout the Holocene. And the geophysical research at the St. Elias Mountain reveals that the Eclipse ice field likely has a continuous Holocene record, and that King Coal is an unrealistic Holocene site. We've been working on depth age profiles for the Eclipse ice field, and it's likely that the site is giving an early Holocene continuous record. So we now have 2 sites in the North Pacific that are likely going to show a complete record for the Holocene. And so with that, I'd like to thank Dan and Betty Churchill. I took some of the GPR profiles at King Coal, and I'd like to also thank the Climate Change Institute, School of Earth and Climate Sciences, NSF, Kalani Research Station, and Icefield Discovery for the support and logistics. I'll take any questions.
In the King Coal GPR record, what was up higher
In the King Coal, these up here,
Yeah.
This is from that stratigraphy that's coming, this is from the profile that's coming off of Mount Logan. So as the ice is flowing over here, it's buckling and changing the ice stratigraphy even on this side of the coal. And so we can see that as it's flowing off of that little increase in slope, it's buckling and creating this problem throughout the whole site. All right, thank you.
Next, we'll have Will Kochtitzky with what causes glaciers to become unstable? An exploration of controls on the surging behavior of Donjek Glacier, Yukon Territories, Canada.
Thanks, Annie. Yeah, I'm excited today to tell you a little bit about what I'm working on in the St. Elias Mountains. Actually fortuitous, I'm coming right after Aaron. I'm going to touch briefly on that, but not too much. I want to give you a broad overview of what surging glaciers are and then kind of just briefly touch on my results. And I hope to instill in you the same kind of passion I have for surging glaciers because I think they're just really amazing features. So glaciers have contributed more to sea level rise than Greenland and Antarctica in the recent past. But in the near future, we know this is going to become the opposite, and ice sheets are going to contribute more to sea level rise than mountain glaciers have. This is causing severe impacts around the United States and around the world. Here's some pictures from the storm in early January in Boston, where you have coastal flooding. In Portland, Maine, we're getting coastal flooding on king tides, and Miami's planning to spend hundreds of millions of dollars to adapt to this. So this is a problem around the world, and if we can provide better estimates to this, we can better adapt to global sea level rise. Here in Portland, Maine, sea level is rising at about a tenth of an inch per year. This is from the Maine's Climate Future from 2015. You'll see the uncertainty here of the projection of where we're going to go. And I would argue basically the uncertainty here is in what's going to happen to the ice sheets. Are the ice sheets going to collapse and we're going to end up at our really high route, or are they going to remain stable and we're going to remain down here? So if we can understand these glacier instabilities better, then we can better predict sea level rise in the near future. And there are 3 different types of glaciers that can become unstable. There are tidewater glaciers. They end in the ocean. They undergo this tidewater glacier cycle that I'm not going to go much into, but it's decadal to centennial in time scales. Ice sheets undergo an instability that's on millennial time scales. But surging glaciers are faster than all of this. They range from 5-year instabilities to hundreds of years. So I propose that we can use surging glaciers as a proxy to understand these other instabilities. So this is one of my favorite graphics of all time. You can see these glaciers in the Karakoram here in high mountain Asia surging. So these little pulses here are surges coming into this larger glacier. So you see these just amazing pulses that come in and it's just like a blah into these tributaries. And you'll notice these glaciers are occurring, these surging glaciers are occurring even when this glacier is not surging. So this is a time slice made by Frank Paul over the last 30 years or so. And so it's kind of a mystery why these surging glaciers occur and do not occur in the exact same areas. So why we study surging glaciers? One, they're just awesome. Here's Donjek Glacier in the Yukon territories. Here's a Donjek River that flows along here. In the past, we know Donjek Glacier has come across here and dammed this river, which has caused a big flood to come downstream. It hasn't done that in the modern era when we've had observations. But I think they provide a really excellent analog to ice streams and tidewater glaciers, and we can actually observe multiple surges of these glaciers. So tidewater glaciers make up about half the area of the world, and so surging glaciers can help us understand half the mountain glaciers in the world. But then these large ice streams that flow in Antarctica and Greenland, they also observe these same instabilities that I think surging glaciers can help us understand. But also surging glaciers in their own right are quite hazardous and they can cause flooding and destruction in these mountain regions. Donjek Glacier is located in a part of the world that not many people live in, so it's not as much of a concern. But in the Caucasus Mountains in Russia in 2002, this glacier here surged and it kind of underwent a catastrophic surge where it rapidly avalanched down this valley and crushed 120 people down here. And so here's the image after. You can see the debris filling the valley now that came out of this glacier. And a couple years ago in Tibet, nine yak herders died. When they came up here, they were grazing their yaks. And actually this glacier surged and it had gone before. But then this was the glacier that came down and crushed these poor yak herders and their yaks as well. We don't really understand why these are happening, and I think this could be ultimately something different from the type of glaciers I'm talking about. But this is kind of an example of catastrophic failure in these surge events. They can also cause flooding. Here's an example from Pakistan from last year. This glacier came down and pinned itself against the valley wall, which backed up the river. The water rose, and then that catastrophically failed, which caused flooding and damaged bridges and farmland and roads downstream from this glacier. So I want to focus the rest of my time now on Donjek Glacier in Western Canada. It's here. We were just learning from Aaron about Mount Logan down here, and then Eclipse Ice Field, which is at the head of Donjek Glacier. The goals for Donjek Glacier for today, I want to try to tell you about some of the how climate change, I think, is imprinted on top of these instabilities that we're seeing, and also kind of start to understand what's causing these instabilities at Donjek Glacier. So here I've mapped the extent of the glacier going back for all the surges that I'm aware of since 1947. And I'd like to give a shout out to George Denton and others who have this terminal moraine date. They dated it from before 1874 from work in the 1960s. And these other dates I've been able to reconstruct from air photos from the Canadian federal government, as well as Austin Post and some others that have taken these air photos. And we can see that the glacier, each successive surge is actually shorter than the last, with one exception. That was 1979 came out further than the 1969 surge. So we see these surges are less and less impressive as time goes on. They become, the glacier is able to advance less. I think this is a climate signal that we're seeing. That because there's less mass balance, there's less total snowfall to move through the system here. So at Eclipse Ice Field, we can get a record of accumulation from the ice core that Aaron was just telling us about. We have a record that goes back hundreds of years. I'm only going to look at this top little slice of it. Eclipse Ice Field is here on Donjek Glacier. I was just showing you the terminus way down here. So this ice core is from 2016, Donjek surge in 1989, 2001, and then 2013. And so this graph is showing you the cumulative accumulation of Donjek as we measured in this ice core. So in 1989, it snowed about 1.5 meters. In 1990, I just add the 1990 snowfall until I get to a surge, and then I reset it back down to 0, and then I add it back up until we get to another surge, and we drop back down to 0. And you'll note they're remarkably similar, just over 16 meters water equivalent that has accumulated at these sites between these surge events. And at first I thought this was great. We've shown accumulation is relating to surging. The accumulation here is just causing this thing to go. And I'd love to talk with others about this more. I think maybe what we're actually seeing is just a decadal average, that the decadal average is basically the same, and because the repeat time is the same, 12 years, you get basically the same amount of accumulation between these surges, and it's actually kind of a disconnected system. And this is important because other people have kind of said accumulation causes surges. There are multiple studies in literature that said that, and so I'm trying to test that here. So some of my brief conclusions from this work I've showed you on Donjek, that these instabilities can occur despite climate change, and they will continue even though we've had a negative mass balance in the region. That I don't really know if accumulation is related to surging or not, and we're working on that with some other ice cores that we're waiting to come in and do the final tally on. I'd love to talk to some other people about how surges are, how we can compare these types of instabilities in mountain glaciers to ice streams. I think I've struggled to make that intellectual leap, and if anyone has ideas about specifically how we could understand the kinematics here as they relate to ice streams, I'd love to talk more with you. And we won't really be able to find out why Donjek surges. I think we can use a lot of the archive of satellite and other data, but it won't surge again probably until about 2025. So it's quite a long time to be studying these, although that instability is faster than most other instabilities in the world. With that, I'd just like to thank Dan and Betty Churchill for some of the support in this, and I'd be happy to take any questions. Yeah, right.
In the mass balance figure, you showed that it was equal mass balance to get 2 different surges. But then before that, when you showed the glacial extent decreasing, you said that was maybe because of changes in climate. So I'm wondering if you could talk about those 2 data sets.
Yeah, thank you. So this is a record from 13,000 feet, I think, or so. So it's actually, we don't get much melt up here. There's some, but I think you're basically, I could show the equilibrium line altitude here as well, and that's also been moving up. So I think there's a negative mass balance, in part because the equilibrium line is moving up, not necessarily at Eclipse ice field. So I think there is less total snowfall on the glacier, which is causing it to retreat here. But at Eclipse ice field, we're not seeing that. The mass accumulation is still the same. If that makes sense. Yeah, Mario.
So, like, to what extent are these glacier surges reflected in the climate policy of some of these kind of climate mitigation policy for some of these polar countries? Because I know about sea level rise and say storm surges, but maybe glacier surges, you don't really hear that and stuff. So what is that like?
I haven't heard of anyone talking about glacier surges in policy. I don't know if other people have, but I think the thing that's really tricky about this, and my work is trying to get at, is can we predict these surge events? Because then you could actually begin to understand and warn people if these are coming or not. And then I think you could have a real impact and potentially save lives like we saw in Russia and Tibet. Just recently, in the past couple of years, we finally, a person, Heidi Silvestre from the UK, she finally identified every actual surging glacier that we know in the world. So this is kind of a really understudied area, and we really are just beginning to understand just where these are located, not to mention how they're acting. So I would love to talk more about that. Thank you.
Next, we'll have Anna McGinn with multi-level governance of climate change adaptation, examining rhetoric and resources from the halls of the United Nations to the hillsides of Nicaragua.
We're going to move away from ice, but probably only momentarily, so I won't walk away from that too far. But my name is Anna McGinn, and I'm a master's student with the Climate Change Institute and the School for Policy and International Affairs. And as Annie said, my project is looking at multi-level governance of climate change adaptation, both at the United Nations and in Nicaragua. And so first I'll be talking about adaptation under the United Nations climate change negotiations, specifically looking at this Adaptation Fund mechanism. Then I'm going to be tracing the Adaptation Fund to a project level, looking at a case study in Nicaragua. I'll look at some of the findings that we look at and comparing these different levels of governance, and then where I'm currently at with my research. So my research stems from attending United Nations Framework Convention on Climate Change negotiations, or what we call UNFCCC Conferences of the Parties, or the COPs. The UNFCCC was established in 1992, and it's the framework under which almost all international decision-making happens on climate change action. At COP21 in 2015, I started following climate change adaptation negotiations, and particularly climate change adaptation finance. Now, adaptation finance is really important because it's based on this idea that countries that are historically responsible for the majority of greenhouse gas emissions should be the countries that are paying for adaptation and mitigation actions in countries that are halting their fossil fuel uses while they're still in the development process, and these countries that are more affected by climate change impacts, even though they aren't responsible for the majority of these historic greenhouse gas contributions. So as I follow climate change adaptation finance negotiations leading up to the Paris Agreement, as well as the 2 years following at COP22 in Marrakesh, Morocco, and COP23 in Bonn, Germany, my goal has been to understand how this climate change adaptation landscape has changed under the Paris Agreement, and look at the roles of different countries and different groups of countries and what role they've played in shaping this landscape. So specifically, I've been following the Adaptation Fund. The Adaptation Fund is a fund that finances projects that help vulnerable communities in developing countries adapt to climate change. And interestingly, the Adaptation Fund was originally created under the Kyoto Protocol. So with the creation of the Paris Agreement, there was actually uncertainty introduced as to whether the Adaptation Fund would continue under the Paris Agreement, or if it would serve out its time under the Kyoto Protocol and then fade away into UNFCCC history. So this was a really unique opportunity to observe how different countries reacted to this fate of the Adaptation Fund. What countries were willing to fight for the fund to continue, which countries and groups were indifferent, and what were the reasons behind some of those. So I'm particularly interested, as I've kind of mentioned, in looking at developing country groups and thinking about what they think of the Adaptation Fund to date. Do they think that it's been effective? Is it the kind of support that they want for the projects on adaptation in their country? And this is really important, again, because of that lack of historic responsibility in most of these developing countries for greenhouse gas emissions. My methods to explore these questions are following these negotiating streams and taking detailed notes of what every country is saying, and then coming back and using qualitative analysis software to go through a coding process of categorizing and sorting and analyzing this discourse. And so what we see from developing countries looks largely like this. The experiences so far have been extremely positive. The fund has never been more in demand and acting on its mandate. We are being sent very, very positive signals on adaptation financing and direct access. And this was stated by the Bahamas on behalf of a group of 134 developing countries. And we see tens of examples of this same kind of rhetoric coming from developing countries. But also we see that developed countries are also seeing this streamlined support and saying things like, we hear a lot of common ground in the room and positive energy about the Adaptation Fund. So what's underlying this clear demand and support of the Adaptation Fund? Well, there's a number of different things, and this is something that I'm looking into more, but some of it is frustration with other funds under the UNFCCC, feeling like all the other ones are more inaccessible. There's also ideas that there's unique mechanisms under the Adaptation Fund that actually are serving these countries well. Can't get into them, but there are ideas of direct access and safeguards. We also see ideas of that the Adaptation Fund was a developing country win back in the early 2000s when it was created. And so there's kind of this political objective of sustaining the fund because they created it originally. There's also the belief that the fund is actually supporting meaningful adaptation in these countries and they want it to continue. So while there's plenty of nuances that I'm not going to get into today, the overarching idea I want you to take away is that basically everyone, and especially the developing countries, are in strong support of this fund. But the question remains, does this positivity reflected at this international level actually reflect what's going on the ground? So to explore this, we have to move from these negotiating tables in the halls of the United Nations out to the field to meet with people at their kitchen table outside. And this multi-level governance perspective requires that understanding what's taking place with any of these projects is that we have to look from the international level to the local level to see if things are functioning effectively. So I selected a project in Nicaragua that attempts to address flooding and drought in the northwest region of the country. And that was my way of looking from this global into the local level. And in using this case of Nicaragua, I asked the question, to what extent does the rhetoric on the Adaptation Fund at the international level align with the realities on the ground? So first, the goal was to see if people are even talking about the same climate impacts. And we find that yes, everyone on the ground is talking about drought as the major impact that they're facing, and that's the same impact that we're really dealing with the Adaptation Fund project, and flooding is an associated challenge that they're also facing. And we hear this directly from some of the interviews and statements like in terms of climate change adaptation. I think the most important thing that we've been able to do is reduce vulnerability to flooding and drought. And other statements like noticing that their well water is getting lower and lower and that they're having to keep deepening their wells. We can also see through looking at yearly precipitation data for Nicaragua that there are some notable very dry or much drier than usual years, especially after the late 80s. So through my interviews though, I started to realize that this concept of multi-dimensional impacts was starting to emerge and be something that was really central to thinking about in terms of thinking about how an impact like drought might be considered when planning appropriate adaptation. So I'll illustrate this for you in a really brief example. In one of the communities that I was in, El Tololamos, they talked a lot about drought, and they talked about the fact that their rain-fed agriculture crops struggled in dry years and that they were definitely low on water, but that really wasn't the majority of their story. The majority of the concerns were that in this community, which is surrounded by big industrial agricultural monocultures, which is pretty characteristic of this whole northwest region of Nicaragua that I'm looking at, those companies put massive pressure on the aquifers, but especially in dry years. And they can do this because they just pay the fines to the national government for overdrawing water. And so that's a problem because people are having to deepen their wells probably even more than they would have to with drought conditions alone. But we also see that the monoculture companies are not planting cover crops during the dry season. And so there's massive dust storms. And the dust storms are causing human health problems and all the dust is landing on the subsistence agricultural farms and inhibiting the growth of those plants. So we're starting to see drought as a problem when we first look at it, but then we realize that when talking to locals, so doing something like installing rainwater catchment tanks might be useful, but it's certainly not going to be sufficient to adapt to this set of impacts that they're facing. Instead, we need to think about some kind of systemic change in industrial agricultural policy or enforcement. And if that's not possible, then at least some kind of systems thinking that's getting us from just thinking about drought as a one-dimensional problem that might have some preconceived solutions to this problem that spans multiple different levels. The next step is to kind of see, and I'm going to wrap this up quickly, but the next step is to think about the extent to which these projects are addressing these multiple different dimensions of impacts that these communities are facing, and if the Adaptation Fund project is doing that in a different way than the projects that might be happening more organically in the community. So I did this through meeting with 5 different NGOs and visiting their projects in this region, and then also going to the Adaptation Fund project. And what we find is that if you're looking, and this is in process, so this is just some preliminary findings, but what we find is that in terms of infrastructure, the Adaptation Fund and these local projects are actually doing some of the same things, especially with these rainwater catchment tanks. But then when we think about the process of how these Adaptation Fund projects are coming to be, that's when we really see some major differences in that the projects that are happening locally have a lot of local investment and a lot of embedded community support, whereas the Adaptation Fund was conceived of, written about, planned for, and funded before these municipalities even knew that they were going to have the project take place there. So the project was pre-formed before the community ever even knew it was going to happen. So with that, we know that I have a lot more work to do to kind of flush out what's going on here with the Adaptation Fund in relation to the local level as well as back up to the international level. But what's clear is that those statements coming out of the UNFCCC are not as, what we see on the ground is not as clear cut as those really positive statements. And this isn't a surprise at all, but it's worth thinking about, because if we're thinking about how adaptation can be done better or in a more sensitive to context way, then if these governments that are ultimately in control of the mandate of the Adaptation Fund aren't pushing them to do anything differently and are only in full support of the fund, then how are we ever going to move adaptation forward to reflect more of what the local communities are needing, and especially this multi-dimensional thinking of what is needed for appropriate adaptation. So with that, really quickly, so far some of my key takeaways have been this consensus on the Adaptation Fund at the international level, this agreement that drought is the kind of direct impact on climate change in this region, but this complicating role of these multi-dimensional impacts, and that we're starting to see this alignment to some extent of local projects and the Adaptation Fund in terms of physical infrastructure, but very different approaches to the process of actually carrying out climate change adaptation. But of course, research is always ongoing. So with that, thank you. And a special thank you to Dan Churchill, of course, as well as Neil Leary, who's here today from where I went to undergrad, Dickinson College, who's been very supportive of my work over the years and allowing UMaine folks to go to the UN climate change conferences. So with that, thank you, and can take questions. Dan.
Are you managing to get any of your findings back to the decision makers? Is there interest in them, and do you think they might have an impact on future policy?
It's a great question. I have contacted the Adaptation Fund multiple times and haven't ever heard back from them, but my hope is that I will be able to get it to policymakers and have it be useful for them in informing future decision making. I also think that going to the next UN meetings, once I've analyzed a lot of my data and maybe have some more to share, I'd be able to talk with delegates there about what I've been finding and kind of hear their views back about, in what I've looked at, does that reflect their experiences on the fund? Neil?
Thanks for the presentation, Anna. So a lot of there's been kind of a shift over time in thinking about adaptation, with a lot more emphasis on community-based adaptation, small scale, working with small communities, a lot of emphasis on very vulnerable, often subsistence farmers or small scale farmers. And you gave this interesting story in Nicaragua where the adaptation that might be most important is how do the small scale farmers adapt to the way the more industrial scale farming is responding and adapting to drought or whatever, and that those are the impacts that are kind of spilling over. How does the Adaptation Fund, is the international system, are they looking at as they try to emphasize for good reasons, supporting what's being done at this very small scale, how that might be overridden by what commercial agriculture is doing, right, in the same agricultural valley in many cases.
Yeah, I think that's a really good question. And everything I've read about this project in Nicaragua is they aren't thinking about the big agriculture that's surrounding the communities that they're working in. So yeah, I think that's one of the major questions is like all these, I think spillover is a great word, spillover impacts or like additional impacts that come from other contexts around them. It's really important. And I think that's one of the challenges in these international projects is that although there are efforts to make it more community-based and community-driven, ultimately, if the whole project is conceived of at the national level, and even if it's implemented by the local people, everything's so preconceived already that it's hard to adjust the project to meet the impacts that the people are actually experiencing.
Thank you, Anna. We're going to move on now to Kimberley Rainminer with a screening level protocol for quantifying risk from organochlorine pollutants in glacial meltwater at the Jarvis Glacier in Alaska.
All right, good afternoon, everyone. I'm very glad to be here and share a little bit of my dissertation work. This is work that was, again, supported by Dan and Betty in Alaska, and it employs the same kind of protocol that I used in Switzerland and Italy, but we'll just be talking about Alaska today. All right, so as a short review of what we're talking about, anything that happens in the world, the closed system, so chemicals that were released in the world stay somewhere on the planet. And in terms of what I'm talking about, specifically to organic chlorine pollutants, chemicals that are released either locally or far away have the ability to volatilize and move atmospherically towards colder, high altitude or polar areas where they can be accumulated in snow and deposited on glaciers and then lost as the glacier melts. So I always say when I talk to the little kids, I just went to a school last week about this, that it would be a really great way to store pollutants on glaciers far away from people if the glaciers weren't melting, but unfortunately they are. To dig down a little bit deeper about what we're talking about today, the organic plant species I'm referring to in this presentation are HCH and DDT. You may have heard about DDT. It was used during my mom's life in the southern United States to get rid of mosquitoes. These both are pesticides. HCH is also an industrial additive. They're hydrophobic, which means that they don't like water, but they really like fats, and that it gives them the ability to bioaccumulate and move through the food chain. They're also persistent in the environment. They really don't go anywhere. They just recirculate. Some of the risks that they carry for humans are cancer, immune system damage, damage to internal organs, and impaired reproduction. And this is just a very short list of many, many risks that I haven't included today. So they're not very nice chemicals. They're pretty nasty. So no one had ever looked for these chemicals in Alaska. As I mentioned, there'd been some work done in Switzerland, some in Italy. There was some work done in Svalbard, but it had never been accomplished in Alaska. So I jumped on the opportunity to join the Jarvis Glacier project and started to look for 19 different chemicals that are noticed by the EPA, that are regulated by the EPA as organic chlorine species. And this is the Jarvis Glacier here on your right. Drill location is in pink, and the meltwater that we'll be talking about in a second is in yellow. This map was also made by Will, so thank you for that. And the Jarvis Glacier is not necessarily great for setting a chronology. There's water throughout the ice, as you can see in this graphic or in this GPR profile. Water is here, but you can also see that there's a significant amount of warm ice. This is the borehole that we drilled the ice that I sampled from. And what that means basically from my work is that there's a high potential for chemical movement throughout the ice. We're not going to be able to get a chronological record of when things were deposited onto this glacier, unfortunately. But remember, this is an exploratory study, so it was enough just to see whether or not we could find these DDT and HCH compounds in Alaska. And they did. So I found both DDT and the metabolites DDD and DDE, as well as HCH, hexafluorohexene, throughout the glacier. So this glacier core went up to 77 meters, and as you can see, there are some trends that I'm not going to discuss here. I'm happy to discuss later. Maybe something, maybe not something, but you can see the species throughout the core. And it's, again, probably due to the high water flux. So then the next step was to find out if any of these species are moving out of the glacier. Now remember that I was looking for 19 different species, and we only found the 2 with the metabolites and the DDT. This is directly down glacier. I did the meltwater sampling, and this is McCumber Creek on the right side. And I found exactly the same types of chemicals in the meltwater sample. So what this shows us is that they're current constituents of the aquatic system right now. So they're in the glacier and they're melting out, they're joining whatever else is in the water, and now they're moving throughout the watershed. So what this then necessitated was a risk assessment. This was the last part of the protocol that I applied in Italy and in Switzerland, but luckily in Alaska I had the opportunity to go all the way through, taking the ice cores, the meltwater samples, and running the risk assessment protocol. Okay, so let me walk you through this map just a tiny bit. So this is where we were, Jarvis Glacier. This is the glacier right here. And then you can see Delta Junction, which we lovingly refer to as DJ, and Fairbanks. And this is all downstream. And then Tanana. This is the Tanana Chiefs Conference region. Subsistence population, predominantly subsistence, and they have a very strong governance structure. Something that's really interesting about the Tanana Chiefs Conference region is that they eat a lot of fish. They're subsistence folks. So in both Switzerland and Italy, where I did the other parts of my dissertation, you've got 1.3 average grams per day fish consumption. It's not very high. Whereas in Tanana Chiefs, you have 32 grams per day average fish consumption, and this is salmon. Now, salmon is a little bit of a fattier species, especially in these colder waters. A couple of different studies done by some of my committee members have shown that they have higher fat concentration. Now, remember, organochlorines love fats, so this adds an additional component of risk. As you can see in the Yukon, Kuskoyokim, right there, 68 grams per day. So this is more of a median study, but it is down glacier or downstream from the glacier that I sampled. So that was the reason that I chose Tanana for this, again, exploratory risk assessment study. So I applied the Environmental Protection Agency risk assessment framework in order to use to do this risk assessment. This is definitely the gold standard globally. To this day, it is the gold standard. Step 1, I've already gone through, hazard identification. So yeah, there is a chemical present that causes health impacts. Step 2 is the dose response assessment. What are the health problems at different exposures? Now this is done in peer-reviewed studies. This is done in a lab framework, testing animals, such things. So that was done by other folks, and then I was able to use those numbers for this risk assessment. Step 3 is what I'm going to be going through now, is the exposure assessment. And this is a really, really important component of this work. Finding out where people live, how much of fish they eat, how much water they drink, how much of the pollutant are they exposed to, and for how long. Step 4 then is the risk characterization. What is the added risk from this chemical? So when I say added, if you don't wash spinach that has pesticides on it, you have some potential risk. If you live in a house with asbestos, you have some potential risk from cancer and from hazard impacts. So this is an added risk from these compounds to folks who are uptaking them. I do want to get to my results, so I'm going to just very briefly go through this. I'd love to talk to anybody about it afterwards. I do love talking about this stuff. Basically, the formula that I use is the long-term uptake is predicated on the concentration within the fish in this specific example, the ingestion rate, the frequency and duration of that ingestion divided by the body weight, and then the averaging time. Non-cancer risk then is predicated on long-term uptake divided by the reference dose. And that's the level of toxic effect. Again, that was set in studies that have been peer-reviewed. And cancer risk is predicated on that same uptake risk times the slope factor. Again, please come back to me afterwards. I am starting to run out of time here. And what I showed was that there was negligible cancer risk, both for 30-year consumers. So let's say that someone grows up and moves out of the area or moves into the area for 30 years, or lifetime consumers, which represents 75 years, from drinking DDT in glacial water. You could just sit there and drink tons of water every day for your whole life, and you would see negligible cancer risk. However, the cancer risk increases 4 orders of magnitude to above an acceptable screening level when average local fish consumption is added. So that means that this needs to be studied further, both on an individual level and with more in-depth research that is not predicated on screening level risk assessments. So this work, I was able to identify new evidence of glacially deposited organic chlorine pollutants in northern North America. This is also the furthest north that anyone has studied this in North America. Identified specific organic chlorine species of concern, and then applied the risk assessment protocol successfully. And what I determined is that future study regions need to include glacial watersheds that do have significant fish consumption, as well as the potential for high levels of organic chlorine species. So thank you again to Dan and Betty and to the NSF IGER and the Department of Defense. I'm happy to take any questions.
Did you partition out the hydrology to determine if all of it's coming from glacial flow or groundwater reflux or hyporheic flow?
Thank you. Yeah, I worked with the team at the University of Alaska Fairbanks, and they did extensive work on that. One of our collaborators published her master's thesis on that. So I used their work, and it was lucky for me, I didn't have to do all of it. Okay.
Next, we have Edna Luz Pedreza Garzon with Understanding the Ecology of Diatom Glacier in Alpine.
So today I'm going to talk about the ecology of the diatoms from the genus Holocene. The first thing that it's important to mention is that this group of algae are organisms of limnological interest because their cosmopolitan distribution and their consistent result or response to changes in environmental factors and catchments allow to determine how the environment affects the aquatic ecosystems, no matter if you are sampling rivers, lakes, or wetlands, and that is independent on the region where you are sampling. The other factor that makes these organisms interesting is the well-preserved conditions of the silica belt. So they become target interest or target organisms for biological studies because the use of these organisms on lake sediments allow to reconstruct the conditions of the climate in the past. So besides the use of these organisms as bioindicators of water quality and current aquatic ecosystems, they can be useful to understand how the changes on climate has affected the current or the past aquatic ecosystems. However, the use of these organisms as the indicator depends on the ability to understand how the changes in the abundance and the occurrence of the species are related. So it's important to understand the responses of these organisms and the sensitiveness of
each of the species that are used in this process. In particular, I'm working with Alacosaida because these species, or the species from this genus, are found on the lake sediments, and the use of these species helps to determine, or usually are associated with variation on the water mixing patterns and also on the water level. However, if you look for the ecological information for the species like Alacosaida lirata, Perclara, Alpigena, or distance, the information is absent, if absent, or there is limited, and they only say these species are associated to oligotrophic conditions of ecosystems. So the gap in the ecological information is a barrier that block the precise and accurate interpretation of the fossil record and the reconstruction of climate in the past. So keeping in mind this bridge, this is the question that is part of my research, like what are the ecological preferences of the species like Alacosaida lirata, Perclara, distance, and Alpigena. And it also makes us consider if the changes in the fossil record in terms of the abundance or the occurrence of these species are related with a real change in the mixing pattern, or just because there is a change in the trophic conditions of ecosystems. So in order to solve this question, and by the help of the funds provided by Churchill Exploration Fund, I sampled during the last summer, accompanied by Benbrook P, 5 lakes on the Beartooth Mountains on the Greater Yellowstone ecosystems between Montana and Wyoming. And particularly, I'm going to present now the results of 2 lakes, Kersey and Beauty, and the results of the distribution of Alacosaida alpigena. During that time, what we did was sampling the 5 lakes during 6 days. We made vertical profile, chemical analysis, and also the experiments. And the current work is focused on the analysis of temporal and vertical distribution of these species and make relationships with chemical analysis. So the partial analysis for Alacosaida alpigena shows that these species have an interesting or contrasting distribution between both lakes, despite the fact that by the time that we started the sampling, both lakes were stratified. However, on Beauty Lake, the distribution or the abundance of these species is constant over the 6 days of sampling, while in Kersey, it is only becoming significant just by the end of the sampling period. And the vertical profile also shows that there is more concentrated, or this species is concentrated on the deep zone of the lake, while in Kersey, it's only presented on the shallow depths. And just the exploratory analysis of this algae shows that temperature, pH, and light in both of the lakes has something or influence the density of this species. However, there are other factors that can influence the result of this study that are not present in Beauty, but can be found in Kersey. So based on that, my next steps on this study are to finish analyzing the samples from the different lakes and to understand the behavior of all the Alacosaida species that I want to study, figure out the preferences of light, temperature, and pH of these species, and if it's possible, try to summarize the behavior in a model that present how the different environmental factors interact
to affect the distribution of this species. Thank you.
Next, we have Mario Williams. Holocene climate, vegetation, fire, and human impacts in Jamaica, West Indies.
Hi everyone, my name is Mario Williams and I'm a second year student of Ecology and Environmental Sciences in the Climate Change Institute. And today I'll be speaking about some recent developments with my work that I've been pursuing down in Jamaica, and also give a general overview of what that project entails. So first, we're again moving away from the polar locations and temperate locations, and let's get situated. So Jamaica is in the Greater Antilles in the Central Caribbean Basin, and it's at 80 degrees north and about 77 degrees west. It's the largest English-speaking island in the Caribbean, and it's about the size of Connecticut, just to get an idea of that physical land area. And it has about 3 million inhabitants. Some of the major economic activities that are done in Jamaica to illustrate that the island has this very tight link with the climate conditions include agriculture, tourism, and then also bauxite mining is very important. So Jamaica ranks 5th among islands of the world for its person plant endemism. Its ecosystems are very highly biodiverse, and there's also a large percentage of wildlife species that are also rare or endemic to the island as well. Major biodiversity threats on the island include urban sprawl. So that aerial photo or satellite image there actually shows the port of Kingston, which is the 7th largest natural harbor in the world. And on the outskirts of Kingston, that is the community of Portmore. So you can see a large built-up developed area in panel A. B, bauxite mining. So as you move across the landscape, you see these large scarred areas where there are these mining deposits. And C illustrates the chopping of wood to make charcoal. And because of this interest in protecting the biodiversity of the island, it has led to the implementation and establishment of many protected areas in the region. And you can see over in the panel on the right in yellow, it shows the location of these protected areas with particular interest being focused on the coast and at the protection of dry limestone scrub forests, which are a globally recognized rare vegetation type. And also along the central interior mountainous spine of the island, where individuals are interested in protecting wet limestone and montane tropical forests. So because of this interest in protecting the island's biodiversity, it led me to hypothesize that there are many gaps existing in the literature and the need for information that would kind of expedite and support this process of protecting the biodiversity. So first, there's the realization that no studies in Jamaica have examined or investigated these 1,000-year changes in the vegetation. So we don't know much about the specific drivers that influence vegetation communities on the island. And secondly, a key component of the research is human colonization of the island and pinpointing when that happened and what impacts are associated with human expansion on the island. So my first hypothesis was that Jamaican vegetation has responded primarily to climate changes driven by shifts in the mean position of the intertropical convergence zone over the course of the Holocene. And we know that the position of the intertropical convergence zone changes as a function of solar insolation. And over these very long timescales, it is a primary control on the amount of precipitation that is delivered to the region. And secondly, Jamaica was first colonized at an earlier date than is suggested by radiometrically confirmed archaeological dates. Jamaica is just south of Cuba, as you saw, right in the region of Puerto Rico. And the existing date from archaeological sites in Jamaica is about 8,600 for the settlement of the Jamaican Taino on the island. And there's a great kind of difference in the dates between Jamaica and Cuba and Puerto Rico, sometimes on the order of thousands of years. So in early February, I traveled to Jamaica and collected approximately 8 meters of sediment from Wallywash Pond. It's located in the southwestern coast of the island. It's about 2 miles inland from the ocean. And it's the island's largest freshwater lake. It's a hard water lake as well. It's super saturated in terms of aragonite and dolomite and some of these calcite minerals. It is close to known archaeological sites. So the Taino Indians, they settled along that coastal area. So in theory, it would be a great site to kind of pick up and detect these impacts that these prehistoric populations would have on the island's landscapes. And it is also located close to an internationally recognized Ramsar protected site. So these are a class of wetland areas that the international community has decided that they are in need of special protection because of the flora and fauna contained therein. While at Wallywash Pond, we conducted a field vegetation survey, and the lake basin was dominated by longleaf pondweed, and it's in that genus Potamogeton, which is a cosmopolitan species. The lake shore was dominated by typha, so a lot of cattails, phragmites, sedges, and grasses. And the upland area was dominated by several tree species, such as logwood and guangu, and these very dense thickets of a plant called Croton humilis, which is pepperrod. Afterwards, I visited the National Lacustrine Core Facility, or LACORE, and this is at the facility at the University of Minnesota, and they store and archive many lacustrine cores that are taken in the United States and all over the world as well. And they also have incredible equipment and instrumentation, which allowed me to collect some great data from these cores. So I got high resolution core imaging, and you can see one of those high resolution images at the bottom of the slide. Pursued initial core description, made several smear slides as well to accompany the core description, and got data on electrical resistivity and also magnetic susceptibility of the sediments. And even though we're at a very initial or preliminary stage of the research, from these digital images, you can gain a lot of information about how the ecosystem was changing. So the lighter layers in this core, based on the image, the digital image, and also the smear slide analysis, we believe that the light layers represent the precipitation of carbonate minerals during a high lake level stand, while the darker layers are organic muds that were deposited during a low lake level stand. So even these images can guide the research from a very early stage in the process. Here at the University of Maine, we'll pursue the examination of different biological sedimentary proxies, and these include pollen grains, and pollen will tell us about how the vegetation was changing at our lakeside. Sporomyella, which is a herbivore dung fungus. It only lives and reproduces in the dung of herbivores, and therefore, if there's more herbivores on the landscape, you will see more Sporomyella spores being preserved in the sediment. Therefore, it is a proxy for herbivore density or grazing intensity, which would be very important given the agricultural history of the landscape to parse out those impacts. Charcoal as well, which will tell us about the prehistoric fire regimes of the area in terms of the fire intensity and frequency of the landscape, and how humans or climate drivers may have changed that fire regime. And also stable oxygen isotopes extracted from ostracod valves, which are highly preserved in the sediment. And based on previous studies, we know that the sediment also has a very high concentration of ostracods. From this research, most importantly, I hope to provide the underground individuals, conservationists, environmental managers who are tasked with protecting Jamaica's landscapes with valuable information about how the vegetation communities changed over the long term on the island. And I also hope to form meaningful partnerships with individuals at the University of the West Indies, some of which we are in close contact with, and also the chief curator of the herbarium at the University of the West Indies in order to facilitate the creation of partnerships between CCI and these local institutions working in Jamaica. And with that, I would like to thank many individuals and institutions that helped me provide technical, logistic, financial support to complete this project, and particularly the Churchill Exploration Fund and Dan and Betty Churchill for allowing me to do this field work in early February. Thank you, and with that, I'll take any questions that you might have. Anyone?
Yes. Is there any similar work going on at the University of West Indies?
Yes. So the team at the University of the West Indies that we are collaborating with is Dr. Michael Vernon. He's their lecturer in climatology at the University of the West Indies, and he has two postdocs that accompanied us in the field, and their names are up on the acknowledgement slides: Kadane Cates and Romaria Anderson. And Romaria Anderson is working in Kingston Harbor, and he's looking on variability in pollutants in the harbor by using sediment cores. And Romaria and Kadane is doing very similar work to me, where they're at this pond that's located on the southeastern coast of Jamaica called George's Pond, and he's looking on vegetation and fire changes in that area as well. So it should be interesting to look at kind of spatial variation across that east-west transect in Jamaica once that work starts to come to fruition.
It's excellent to have our institute involved in something in the ITCZ, since we don't do much there, and it's really important understanding how it changes with respect to the other circulation systems. So it'd be great to talk to you more about pursuing that relationship with West Indies.
Yep. Thank you.
To this day, I run into the classrooms chapter from time to time. I think that after all these years of doing it this way, well, yeah, geologists were more slime people. Atmospheric scientists were more overhead. I use overhead. I was like overheads because I could make them last minute. You didn't have it ahead of time. Still slide. Yeah, oh yeah. No, until the early 2000s. Good job, music in an auditorium. Whatever, probably a history. Who is it, dear friend? See this happen so much, I took the screen off. I saw him leave the top, started turning over. Well, I can say you can hear all this.
All right, everyone, thanks for your patience. Next, we'll hear from Jeff Auger. He's going to be talking about climate evolution in the Arctic and North Atlantic during the last 2,000 years.
Thanks, Andy. My name is Jeff Auger, and I will be talking about the climate evolution within the North Atlantic sector of the Arctic. So just a quick outline, my major question is just that, how has the climate evolved in the North Atlantic sector, the North Atlantic and the Arctic? But the major problem here is that there's the observations within this region is very scarce. So to help to solve this problem, we use climate reanalysis models, which are atmospheric models that are constrained by observations, and climate proxy records, which we'll be hearing a lot about throughout the next couple of days. So a couple other questions that I'll be looking at with these proxy records are, do the medieval climate anomaly and the little ice age show up within each region, each proxy record, and are the changes from one anomaly to the next simultaneous across the whole domain? So the state of the Arctic and the North Atlantic climate, we know that the Arctic is warming at nearly 2 times the rate of the global rate. And we can see this using reanalyses. This is ERA interim, going back to 1979. And we can see that the early 2000s subtract the previous 2 decades, that there's a pretty strong warming in the Arctic. We can go back further with JRA 55 to 4 decades prior to the early 2000s to see again that there is warming within the Arctic. And using 20th century analysis, we can go back 13 decades prior to the early 2000s. And again, we're seeing this warming is evident. So my question is, how about the 200 decades or 2,000 years prior to the 2000s? So there's a lot of literature that discuss the links between the Arctic and the North Atlantic climates and how the changes in the Arctic are influencing changes in weather patterns and climate patterns of the North Atlantic. But all of these are discussing more modern linkages. So I'm going to be basically extending this for the past 2,000 years to see how these linkages have appeared in the past as well as the more modern times. So we've seen temperature. I'll be showing precipitation really quickly. These are the 3 reanalyses that I showed before. And we can see here that looking at the early 2000s, subtract the relative cooler period of the 1980s, that there are some changes. There's more precipitation at lower latitudes, and then there are some, this is a more coarser resolution model, but with more finer resolution models, we're seeing that there are some changes in precipitation within the domain. However, we're not seeing a lot of changes within the Arctic, but this is, again, these are constrained by observations. There's not a lot of observations, so there might be changes, we're just not seeing them in the reanalyses. And finally, we can look at the atmospheric circulation. This is the mean sea level pressure. So this is the near surface circulation patterns. And we can see in the winter months, the Icelandic low here and here
is stronger than during the summer months, and that the Azores high is stronger during summer months relative to the winter months. But the difference between these two pressure systems is gives us the North Atlantic Oscillation Index. So moving toward the proxy records that I'll be using, so far I've looked through hundreds of proxy records and had to kind of whittle down to a more robust data set. And so I've created, using these requirements, the records have to be at least 500 years long. It is ideal if they overlap local observations, but it's not required. The temporal resolution has to be on the order of, has to be less than 5-year resolution on average. And each record has to be previously calibrated to observations or other reconstructions. So this has given me 36 climate proxy records over this domain. Each one is correlating to either one or two of these climate variables. Some are temperature, precipitation, or atmospheric circulation. Again, the circulation is more or less the Icelandic low, the North Atlantic Oscillation. And this has become a multi-proxy attempt at understanding the climate over the past 2,000 years using barbed lake sediment cores, ice cores, speleothems, and ocean sediment cores. So one way of looking at the proxy records is through empirical orthogonal functions, or EOFs, which is a special case of principal component analysis. EOFs incorporate time. So we can look at the first, basically the first principal component, or EOF, and we can get a time series of that principal component, or the EOF. And as with the case of PCA, there's also a principal component analysis. There's also one EOF with each record that you incorporate. So I've done some manual clustering on locations and which climate variable that they're associated with. So we can see the Arctic Canada temperature, Icelandic low are the yellow dots, North and Baltic Seas precipitation in purple, and finally Finland summer temperature in black. And we can see here that there are similar trends. The medieval climate anomaly we can see in the Arctic Canada. We can see here in the second EOF, the Icelandic low. We can see in the first and second of the precipitation in North and Baltic Seas. And then we can see the transition into the Little Ice Age for each of these locations or climate variable. But for Finland, summer temperature is not as clear. So some of these are very obvious, and then others it's not as obvious. Next, we can look at these through the wavelet power spectrums. These are basically this imposes a sine wave onto the time series, and where the sine wave is squished, the time period is going to be shorter. So shorter time periods up here, longer time periods where that sine wave is elongated, showing longer time periods for the cycle. But if we can see, as I add color to these, that the changes in the periodicity are occurring over warmer or cooler periods. But again, this isn't extremely clear in some of the other proxy records. However, this proxy record, we can see that there is a very clear peak at the 32-year time period. So looking at that same record, the Agassiz ice cap in Ellesmere Island, we can I can show the running standard deviation over 20-year time periods overlay this onto the wavelet power spectrum plot. And we can also see that with each red blob here is that there's also an increase in the standard deviation. So what I will also look at is extending this power spectrum down to centennial scale time periods instead of just multi-decadal time periods. So with this, what's the overall picture of the climate evolution within this domain? Well, it's still a little complicated. Some of the records are showing very clear periodicity changes or a clear transition from the medieval climate anomaly to the Little Ice Age. However, some are not as clear. Another thing that I can be looking at with these the wavelet power spectrums, though, is that I can draw a line through one period, one periodicity, and create a time series of that time periodicity. And this would give me, we can kind of see that there are going to be increases of the power of this time periodicity, and then decreases. So this might be able to, I might be able to link this to findings of was the time periodicity stronger or weaker during the medieval climate anomaly? Is there a transition into the Little Ice Age? And finally, the last step is to compare these results with the paleoclimate reanalysis, or Paleo-R. This is an atmospheric reanalysis that is constrained by proxy records instead of observations. And so some of these proxy records might be a part of this model. And so I can compare to this Paleo-R to find where there are differences or where they compare well through time. This is extended back to 850, giving me a much longer time period than more modern reanalyses. And with that, I will take questions. Thank you.
I appreciate it.
Next, we'll hear from Laura Hartman, microanalysis of tephra from the cold Nefeti ice core.
Thank you, Annie. And I'd like to preface this talk with telling you that most of my work has focused on tephra investigations in the South Pole ice core, which is in Antarctica. But I was put onto this project to hopefully identify tephra in the cold Nefeti ice core. And in addition, if you were at my brown bag talk last week, this will be repeated information, so I apologize. So first, I'd like to say thank you to all of my collaborators, my committee, co-authors, etc., in no particular order. Without their help, none of this would be possible. So thank you to them. So as I mentioned, I investigate tephra in ice cores, and this all starts at the volcanic edifice. So when a volcano erupts, gas and ash is ejected into the atmosphere. And the location of the volcano geographically, as well as how powerful the eruption is, dictates whether or not that the ash and gas ejected into the atmosphere has a climatic impact. So you have, here we go. So you have a volcano that is ejecting, here's your volcanic column, and here's your ash and gas cloud. And so say you have a large volcanic eruption, like the 1815 Tambora eruption. So that ejected a large gas and ash cloud into the atmosphere. It went into the stratosphere and subsequently circulated globally. So that means that this eruption, the 1815 one in Tambora, had a global climatic impact. So what does that mean? So the ash particles that were in the atmosphere are interacting with incoming solar radiation and reflecting that back out, so thus cooling the planet. You also have smaller eruptions that don't quite eject into the stratosphere, and those are generally smaller, but they do have a small climatic impact because, as you can see in this graph, the lifetime of those clouds is 1 to 3 weeks. And by clouds, I mean sulfate and ash primarily. So how do you investigate how past volcanic eruptions are impacting the climate? So one way is historical information. So somebody saw this large eruption occur and wrote it down on a piece of paper or papyrus or rock or whatever their method is. Other ways is to investigate tephra, which is what I do. That is in peat cores and sediment cores, and also ice. And I'm not going to mention the peat and the sediment because I focus on ice, but that's just as an FYI. And the other thing about ice that is sort of unique is that it captures the gases that are also emitted. So this is a sulfate record from Legrand and Delmas, 1987. And they indicated on this sulfate record several spikes in the sulfate record that they think are attributable to a volcanic eruption. So as I mentioned earlier, the Tambora 1815, that's this spike right here. However, the tephra that I mentioned, which is the volcanic ash, is not always observed with these corresponding sulfate signals. So the question is, okay, is the sulfate and the ash cloud traveling separately due to physical properties of each one? So one is a solid and one is a gas. Or is there some kind of sampling bias? So in my lab, previous students have investigated capturing, methods on capturing the particles. So the first one is, which is still used, is filtering. So you take a selection of ice, you melt it down, and you filter it using micropore filters. The problem with this is that after you mount that filter and put it into your microanalytical instrument, when you take that out, the particles aren't necessarily captured still in the filter because they fly away from the vacuum. The other thing that was tried was the filter with the sticky tape, so they use the same thing. They take an interval of ice, they melt it down, they mount it on a filter, and then they take a piece of tape and try to mount the filter on the tape, so now you have particles on tape. But the problem is that it captured large particles, but not small ones. The other possibility is carbon planchets, but the problem with this is that, well, at least the carbon planchets that we have are about this wide, and the particles are spreading throughout that entire surface, so it's hard to identify particles that are way out here when you're over here. And yes, you can analyze the entire thing, but that takes an awfully long time. So in my lab, we developed this method for mounting particles in epoxy, and without going into it, basically we have a piece of tube that comes down and mounts the particles in a very tiny mounting surface, which is a lot smaller than the carbon planchet method. And it allows you to analyze particles or insoluble material from ice in a smaller region. I'm not saying that this doesn't take a long time, because it does. Probably, for me, about 3 to 4 hours per mount. But that's better than this method, at least in my opinion. And if you want more details on this, we can chat about it later. I just don't want to go into it for the interest of time. So, okay, we have particles on our epoxy mounts. How do we analyze? We use microanalytical techniques, and traditional method is using the microprobe with wavelength dispersive spectroscopy. And the way that this works is that the electrons originate in the column, and they travel down, being focused through several lenses, eventually interact with your sample at a specific sampling volume, depending on how powerful this beam is. And that sample emits characteristic X-rays based on the elements that are present within your sample. And those X-rays are coming off of your sample like this, and eventually interact with this crystal, and they are diffracted from the crystal to the detector, which gives you chemistry. So on microprobes, this crystal and this X-ray move with the elements that you're trying to analyze. So the problem with this is that you need a longer sampling time. So it takes about 7.5 minutes to analyze all the elements that we're interested in for our samples, which can be an awfully long time for a tiny particle. And in addition, we don't always have the most ideal sample surface. So for this method, you need an ultra flat surface to analyze when this beam interacts. And yes, you do need that, and ideally you will have that using this other method that I'm about to talk about. But because of the way that this detector works, we showed in our lab that it's a little bit more forgiving. So as I mentioned in our lab, we've started to kind of use the Sem Eds Analysis as our workhorse. And basically the way this works is the electron beam comes down, interacts with your sample, X-rays come off, and basically go into this bucket collector. So instead of having to move the crystal in the detector, you're moving nothing. It's just all going straight to the detector. So in that way, it's a little bit more forgiving. And then in addition, when I first arrived here, we were using a standardless quantification procedure. And basically the way that this works is that some kind of correction factor is imparted on your sample, and we have no idea how that works. So while I was here, we moved to this new standards-based quantification procedure, which is fully quantitative and has no black box quantification correction factor. So which one we use is determined by particle size, but we primarily use this. Okay, so now we know how we're going to analyze. Now we need something to analyze. And as I mentioned, for this talk, I was given, well, not for this talk, but I was given sections of the Cullin-Feddy ice core to analyze and try and find tephra to use as a time stratigraphic marker for that ice core. So the ice core is located on the Swiss-Italian border in the Alps. And the location is good to investigate the interaction of humans and the environment in the past. And one published example of this is a Black Death era lead development. So basically, in the glaciochemical signatures of the Cullin-Feddy core, they saw a large decrease in lead during the Black Death period. And they're attributing this, so humans in this area were ejecting a lot of lead pollution into the atmosphere, and that is seen within the core. So back to tephra. So I'm trying to find these tephra particles in these three intervals, which were identified using glaciochemical signatures. And basically in the shallowest section, I found tephra, which was analyzed using DTSA. I'm out of time, so I'm going to forward through this. But if you have a question, I do have a poster in the back that basically talks about all of this. So just to kind of finish up here, several eruptions were investigated using the chemical analyses as well as the timing of the tephra within the ice core, which was determined using annulator counting. And we suggest that our tephra is consistent with an unknown eruption from approximately 536 CE. And using this chemical relationship, we're saying that it's consistent, all of the unknowns are consistent with an Icelandic eruption. So with that, I'll say thank you again, and sorry for going over.
We're going to hear from Charles Rado now, a 1600-year ice core chemical record from Central Asia.
That's not what's on the schedule. All right.
Hello, everyone. I was a late addition to the schedule, so sorry if you did not anticipate this talk. I'll try not to get you too late to your coffee break. So I'm a member of the Ice Core Research Group. I'm going to be talking to you about a 1600-year chemical record that colleagues and I are coaxing out of a new ice core from Central Asia. Unfortunately, I missed this symposium last year with bilateral pneumonia, so I'm going to give you last year's talk in 3 slides at the beginning so you understand why we're so excited about this new record. There we go. So I'll be focusing from last year. I'll just talk briefly about Central Asian seasonality, how moisture delivery to Central Asia varies throughout the year, and why that makes our preliminary data from Central Asia, so this new ice core is so exciting. So Central Asia in a nutshell, we're focused on the 6 countries of Central Asia, sensu stricto: Kazakhstan, Uzbekistan, and Turkmenistan in the west, low-lying, very, very arid countries. Kyrgyzstan, Tajikistan, and Afghanistan in the east, high elevation countries, glaciarized, particularly Tajikistan and Kyrgyzstan, have high elevation glaciers, over 5,000 meters. So there's some fundamental differences between how moisture is delivered to this region. You can see in the west, in the lowlands, there's almost no moisture, under 25 centimeters a year through most of that region. Most of the precipitation in the region falls, you can see in the east here, in the glaciarized parts of Kyrgyzstan and Tajikistan, water equivalent of 50 centimeters a year in the highest areas. Unfortunately, this is where all of the grains that feed Central Asia are grown. So they are completely dependent on meltwater that comes from the highlands during the warm summer period. Both natural communities and human communities need that meltwater for irrigation or for any other uses that they have. The reason we're so interested in seasonality here, you can see purple is the Tajik moisture record, Kyrgyz record is in red for these curves. There's this 6-week critical overlap in the spring where it's both still cold from the winter and where the wet season is kicked up. That's when the moisture delivered to the highlands as snow falls on the ground, and that's the water tower that Central Asia has for the year. Precipitation falls to almost nothing during the long summer warm season, and they need that moisture in the lowlands to grow any crops they need. And of course, natural biotic communities need that as well. Nothing good has happened in the 20th century in terms of that moisture budget. You can see on the left here is precipitation trends. Every country is getting drier in Central Asia. Again, red and purple, Tajikistan and Kyrgyzstan, the water tower countries are getting drier fastest, and every country is warming. So there's a concern that this critical spring season where the moisture is delivered, the circulation patterns bringing that moisture are changing. So to look at the total scale of how that circulation changes over the last 2,000 years, I analyzed basically every proxy record I could find for the last 2,000 years. This is a paper that we have in review right now. I'm happy to discuss the gory details, but it's a big one. The take home here is, while this may look like a lot of records, this is everything for 2,000 years in Central Asia, and the resolution is not great. For our purposes, these are century to, at best, decadal scale records for the most part, so we can't look at phasing, seasonality changes. We can see that the onset of the Little Ice Age was relatively rapid, but we can't characterize that in terms of number of years. So low resolution records and very few. The Little Ice Age is sort of is our current focus as we are beginning to analyze our new ice core. Focus on it here, it's in blue. The interesting thing about this is the most major climate reorganization in Central Asia, or the most recent, I should say, climate reorganization in Central Asia. It's the one we have the best resolution on, and so one we'll have the best resolution on in the new ice core record that we're generating. It also, at the onset, you can see right here, there was a temporary change in the climate moisture delivery to Central Asia. For a very brief period of time, moisture came in differently, came in from the Mediterranean in a way that it hasn't really in the previous 1,000 years and hasn't as much since. And so we're interested in characterizing the onset of that event and what it can tell us about changes in atmospheric circulation during reorganizations, how fast they happen, and what they will look like in the chemical record. So to get a better resolution on that historical variability in Central Asia, colleagues went to the Tajikistan-Kyrgyzstan border in 2016 and drilled a 37-meter core to bedrock from a plateau in the Pamir Mountains. That core was then transferred to Alfred Wegener Institute in Bremerhaven, Germany. Some of the colleagues there did initial measurements, electrical conductivity, magnetic susceptibility, these sort of physical parameters in the core that give us a first order understanding of total chemistry input, dust input to the core. Then Jeff Auger and I split the core lengthwise, distributing sections to our various collaborators on the project. We brought home this red center region for us to do our chemical analyses on here at CCI. I should also point out that an archive luckily was retained in Avi future needs. So here we measure the core, we're measuring chemistry in two different ways. We use the laser ablation system you guys have probably heard about here in the past. What that gives us is 500 measurements per centimeter. At the top of the core, that is that's sub-daily scale for the most modern ice. And even back to the beginning of the Little Ice Age, we have sub-seasonal, in fact, storm level measurements up back to the beginning of the Little Ice Age using that. That's time consuming and would not necessarily give us a first way to look at the core. So we had done targeted sections of that to begin with. The rest of the core, the nice thing about the laser is that it's non-destructive. So we still have the whole split that we brought home to melt. That we put into the continuous melter. We've melted the entire 37 meters of that core. And we have co-registered samples for ICP-MS, our resolute ICP-MS measurements. So that's our 29 chemical species that we've measured so far. And we have co-registered samples to do IC measures and an archive that we will probably end up using for tephra particles or something like that in the future. That's at 1 centimeter resolution. So even back to the beginning of the Little Ice Age, we have annual type resolution in that record. Obviously don't have anywhere near the time to give you 29 elements, but I'll give you kind of a select data and show you why we're so excited about what we're seeing in the chemistry that's coming out of the core. This is just two species, uranium and lead, ones that I had plotted up because I was interested to see what was happening in the 20th century. The blue box here is the Little Ice Age, this is the modern surface to the left, older to the right. You can see at the onset of the Little Ice Age, we have an increase in chemical delivery to Central Asia, and increased variability in the record. At the bottom, you see the isotopic record, stable water isotopes. Again, you can see a continuous, for about 100 years, decrease in the, there it is. Right in here, you can see that the chemistry is becoming more depleted for about 100 years up to the onset of the Little Ice Age, and has a sudden jump to less depleted values during that transition. The middle here shows you the sections that have already been lasered, and I'll talk about those in just a second. Given the temporal resolution we're looking for in this record, the most important thing for us to do at the beginning is to get an absolute age on this record. We want a plus or minus 0 years calendar attached to this if we can. The first step is to find known age events in here. This is the volcanoes that Laura just talked about. We've been able so far to identify 4 of the most major eruptions in the last 2,000 years: Krakatoa, Tambora, Somalis, and Chengbaishan. So we have those layers in the core absolutely dated using permittivity and conductivity, so the total dissolved and dust input to the core here, and then looking at both the principal component analyses of some chemistry, bismuth, arsenic, and sulfur that come out of volcanic eruptions, as well as the raw data on those 3 elements. So we have those 4 layers are absolutely dated, as well as, of course, the modern surface. Between them, we can count years using annual chemistry that comes out of the laser ablation record. In blue here, you see the calculated layer thickness. That's using our understanding of moisture delivery to the glacier and how glacier dynamics works. We have an expected annual layer thickness. Then we go to the laser data. The next slide will be that purple box. And you can see that in an area where we expected to find annual layers approximately 2 centimeters thick, we find regular, in this case, 5 order of magnitude spikes on the same spatial pattern, giving us a first order understanding that these are in fact annual spikes, and we can use these. We have 8 different chemical elements that we have these records for to count annual spikes between our known age date, between the known volcanic horizons in the core, letting us put a very high resolution time scale on our core. So our next steps will be to fill in the last of the chemical gaps in the record. That includes all of the ion chromatography and getting melter data back from the sections that have been reserved for laser measures. Well, I'm going to be going to Germany in a couple of weeks to retrieve the archive so that we can laser the entire portion of the core that records the onset of the Little Ice Age, so that we can get a storm an individual storm event level record of that transition. And our 29 species ICP-MS data is at high enough resolution through the 20th century that we'll have seasonal scale understanding of those changes, so including anthropogenic or other modern changes. Thank you.
Thank you. Some colleagues and I have done some work in that part of the world that gets more recent drought since about around the year 2000 to the present. And yes, you see this, like as you correctly say, the moisture coming in from the west and sort of the orographic capture of the mountains. But we also see there's a linkage to sea surface temperatures in sort of the eastern Indian Ocean and the western Pacific that effectively generate waves that move westward into the region. So, and that can modify the storms as they come across. I'm very interested in this to see how this transition is very interesting to me. So I'll be bugging you.
Excellent. Thank you.
And for the final speaker before our break, we have Sarah Hall. She's going to be talking about glacial geochronology of the northern Peruvian Andes, relating 10 exposure ages from the Cordillera Blanca in Peru.
Thanks. I'm Sarah Hall. I'm a geoscience faculty member at College of the Atlantic in Bar Harbor, Maine, and I'm kind of a generalist. I teach classes in geology and climate, but my training is in geomorphology, and most of the time I'm studying tectonics, but earlier in my PhD, I started studying paleoclimate through glacial geochronology, really 10 records of glacial geochronologic features like moraines. And while I was at McGill University before coming to College of the Atlantic, I was working with some graduate students on this beautiful crustal scale detachment fault in the Cordillera Blanca of Peru. And we were driving around this amazing range that had beautiful moraines, and I realized that there's an extraordinary record that many people have worked on, but sort of only in one small quadrant of this larger range. And I was struck by the varied morphology of the range. And so this study began about 10 years ago. It's kind of embarrassing how long it's taking, but it's a study that I was doing mostly with undergraduate students at McGill who were field assistants. And now, as I've come to College of the Atlantic, I've designed a field course where I take students to this region and they do some of the GIS work. And Brenda Hall and Aaron Punneman have invited me to continue doing some of the plasmogenic processing in the lab here at CCI. So that's what I've been working on for the last year. And thanks so much to the grad students in that lab who've helped me out a lot getting going here. So there's only 9 samples that are finished at this point, but there's 30 more that are being run at Livermore right now, like today. So this is just an update. It's supposed to be 2 minutes, so I'm using all the time right now. So the Cordillera Blanca in northern Peru is right up here. Currently houses the largest volume of tropical glaciers in the world. It spans a couple degrees of latitude. There's this major range-bounding fault here on the western side of this range. And the morphology from the northern part to the southern part of the range is quite different because of this major crustal feature. So as I said, there's been plenty of studies of the modern and paleo glaciers in this region because there's beautiful moraines. This is the Cordillera Blanca up here, and most of the studies have been focused in this southwestern part of the range because there's textbook, beautiful cross-cutting moraines. They're easy to just drive right up to, snag a sample. But this whole northern and eastern side of the range, there's no data from currently. There's a few ages in the northern western side, but that's it. There's some data further south in the Cordillera Huayhuash and the Junín Plain, and because there's this international effort to catalog all the paleoglacial signals all along this Cordillera, not just in South America, but all the way from Alaska to Patagonia, there's a number of data sets to compare the glacial advances up from the western and eastern sides of this global Cordillera. So this study now encompasses and trying to combine the whole area. So I'm not duplicating any samples already collected down here, but instead focus my attention to mostly the eastern side of the range, where there's now a nice road to get over there. So just in the last few years, we can get there. Like I mentioned, there's morphological variation along this range, largely because of this fault. But there's also, you can see most of the glaciers are in the northern part of the range, where valley hypsometry suggests that that's where the largest accumulation areas are right now for the modern glaciers. And then there's very little ice extent in the south. This is where most of the current studies come from. The fault itself is inconsistent along the range. It's very fragmented in the southern portion, one segment in the central section, and kind of less easy to follow in the northernmost section. And there is a small precipitation gradient across the range from east to west, although the main precipitation gradient in the Andes is further to the east, right at the first break in topography where the Amazon basin is far to the east, and then the western side of the Andes is mostly hyper-arid. But there is this little precipitation gradient across the range, so it really begs the question, are the paleoglaciers getting to the same elevations or reaching the same distance from the range crest as on the western side, as we've all sort of assumed, because that was the only data we had. So I targeted 2 transects. I wanted to do a transect from west to east in the north, and then one in the south of the range, using some of that data that already existed from the western side and not duplicating it. So I sampled I didn't sample. A lot of my undergraduate and graduate students sampled all over the range, and I preferentially planned to prepare samples from the northwestern, northeastern, and southeastern side of the range. And these first 9 samples that I processed were just 1 or 2 from each moraine, just to see where we are. What am I able to find on the eastern side, where the moraines are less well preserved, some of the same ages that we can see very nicely in these southwestern valleys, where the moraines are preserved very well. So I said that the valley morphology is different along the strike of the range north to south, but they're also really different on the western side compared to the eastern side. The western valleys are classic U-shaped valleys with huge pampas that store groundwater. There's really nice moraines preserved in the valleys, and especially out on this flat plain that's the detachment basin for that normal fault. So the moraines are very well preserved there. The eastern side, you can see the morphology is kind of more fluvial in nature. There's more V-shaped valleys, and the moraines are just limited to these little flukes that have not been re-incised into. So it was a challenge to find good sampling, good boulders to sample on the eastern side. So the 9 samples I have, there's 2 that fall in this 140 to 180,000 year range from the northwestern side of the range. And Farber et al. In 2005 collected some samples from these large moraines in the south, and they see ages that range from 80 to 400,000 years. So this is within this, they do see a moraine right at the same time, marine isotope stage 6, likely related to that advance. And so I'm excited to find a tie point in the north, so I can see that same advance in the north. And then in the southeastern portion of the range, I have a number of new ages that are all mostly late glacial and younger during the Holocene. And these are at the same time, so these black lines are my ages, and I've overlain them on a new study by Nathan Stansel et al. In 2017, which is a study of just one valley right here. He sampled all the moraines and cored the bogs of one valley, and I see that my samples fall right around the same time as a lot of his cosmogenic ages. So here's his spikes of his cosmogenic ages, and he noted that from valley to valley, there's a lot of variation, just where the moraine positions are, even though the ages are the same. So I did expect to find that my ages should duplicate what we see in the south, but likely follow a slightly different position within the valley. So in the end, I'm trying to not only add to the paleoclimate record for this range and the larger transect along the American Cordilleras, but I also am interested in seeing what I can learn about the different morphologies of both sides of the range, given this major crustal flow and the asymmetry of the glacial erosion from the north to south across this range. Oh, and that's it.
All right, so that concludes section 1, and we'll be leaving the presentations for the second session, and during that time, we'll have a short break. Thanks, everyone.